Okay, so in the class today, we're going to talk about the data model used on the semantic web, which is principally RDF. It's something that we also see in databases, or that I teach in my section of databases. So in general, as we spoke about, the idea of the course is to talk about this evolution of the web towards the semantic web. And we spoke about how to implement that in the first class using data, logic, or ontologies, queries, and okay, then we can receive directly output for complex queries on the web. So today we're going to focus on the data aspect. So the data aspect is a proposal for how to model data on the web is this resource description framework, or RDF. So how does it work? Well, it's been standardized since 1999, 2000, and there was another version in 2004, and the most recent version was recommended in 2014 by an organization called W3C, Worldwide Web Consortium. And this is a body that's responsible for lots of web standards, for standardizing lots of aspects of the web. So it's a web standard. So how it works, basically, RDF is based on triples. So it's kind of similar to what we see in the example here: Ireland, part of Europe, Ireland, capital, Dublin, and so forth. So we have essentially, we're going to model data using triples. So we call these triples RDF triples, and they have a subject, a predicate, and an object, which is sort of similar to a simple form of natural language. So subject, predicate, object. It seems very simple. Like, can we really model, the web with this model, with this simple data structure? And the answer is that indeed it's sufficient to be able to represent data. So we can represent arbitrary amounts of data, types of data, as triples. If we wish to integrate new data, for example, we wish to add new information, we can just simply add more triples. So for example, here, we've added an extra triple to say Dublin's population has a population of 1 million. RDF can then be seen as forming a graph, where every triple here forms an edge in what's called a directed label graph. So we have directed edges. So we have an arrow, and we have labels on the edges to say what type of relation that edge represents. For example, that Ireland is capital Dublin. So RDF, this triple based format, is essentially a graph-based data model. Okay, so every triple forms an edge in this graph from the subject to the object with an edge labeled predicate. So often we refer to, or even in the standard, it refers to a set of triples as an RDF graph. Okay, so this is essentially what has been proposed as a data model for the web. And an interesting question then is why graphs? Why not use relational databases, tables with arbitrary number of columns? Why not use trees, or why not use something else entirely? So why graphs? It's worth kind of explaining that in a little bit more detail. Any questions on this so far? Okay, so I use these slides as well in some other courses, but in case you haven't seen this before, it's kind of my explanation for why graphs are sometimes a useful data model, and principally because they offer a lot of flexibility for modeling. So if we think of modeling data in general, the standard way is to model data as relational databases, where we have these nice clean tables and we can file away our data, and our tables are in normal forms, and everything is defined by a relational schema that defines all the keys and so forth. So everything's very structured and ordered. But it might often be difficult in certain cases to organize our data in such a clean way. Um, so here we have some, an example of a typical use for relational databases, which would be, for example, in a bank to manage information about different accounts and clients and exchange rates and so forth. And we can define IDs and have transactions to make sure everything works okay and we never have corrupted data or inconsistent data. So in this case, we know more or less, because it's a bank, we know more or less the kinds of data that we're going to want to store, and this isn't, going to change so often. However, if we were to take some other domain where we don't know what we would like to store in the database, it could be a bit more difficult. So for example, let's say we wanted to create a database about planets, and we didn't initially know what we want to model. So where do we start? Well, we could start with maybe, for example, the names of different planets. That's a pretty good starting point. And then maybe we could eventually incrementally add some more columns, like the distance from the sun relative where the Earth is 1. And we could continue adding more data and columns and so forth to our table until we have maybe a full table of different attributes of planets and their values. So their radius, strength of gravity, length of their days, the years, temperature in Kelvin, and whether or not they have a ring. So this seems pretty fine so far. This is a nice table. All's looking well. So what happens if we want to model some satellites, the natural satellites of planets or moons of planets? So, okay, this seems a bit trickier, because if we try to add another column here, as we've been doing, some planets don't have moons, which this is a null here, symbol for a null. Some have multiple moons and so forth. So the standard relational database answer to this, what do? We rather define it as a different table, right? And that way we can model different multiplicities. So we can have we can represent planets with no moons, planets with more than one moon, and so forth. So here we have our moon table, name of the moon, and the planet of that moon. Maybe we want to add more information, like who discovered the moon, what year it was discovered. So in this case, we see that, okay, well, what do we put for the moon of the Earth, which I've written as Luna here? And maybe there are some other moons for which we don't know who discovered them. So, okay, we apply the same recipe as we considered before, which is we break it down into multiple tables. So here we created a separate table for moon discoverer, where we can omit the moons where we don't know the discoverer or doesn't have a discoverer. And we can add a separate table for the discovery year. So, okay, maybe we could combine these if we always have both, but this way we can avoid some nulls. So here we have a problem, because we've mentioned the planet is Terra, and here the planet name is Earth. So we have this sort of inconsistency in our data. And in the context of relational databases, how we would solve this is, if we wanted to make sure that all the planets here are really planets according to this table, is define a primary key, a foreign key, sorry. So we would say that this here is a reference to the primary key of planet name. So all of the elements here must appear here effectively. And in this case, we have no option but to define this in a consistent manner with this table. So all is well and good. But now some people have decided, unfortunately, that Pluto is no longer a planet. So we need to think about this. So how are we going to represent now that Pluto is not a planet? So we have this last column, or this last row here of our table, that no longer makes sense. So we don't want to just delete the row, because we have all this useful information. So, excuse me, there's a couple of options. What we could do is define a new table, dwarf planet, and in that we can add our Pluto row to distinguish it from all the other planets here, which generates a problem. And the problem is, if we look here, we see that Pluto no longer is referenced by this primary key, by this foreign key, so it no longer appears here. So this is going to be inconsistent, which generates further problems. So it's essentially, what are we going to do? Probably the simplest thing to resolve this, since Pluto is no longer here, would be to remove the primary key. There are maybe some other tricks we could try to apply, but by far the simplest would be to just essentially remove the foreign key constraint, which we liked, which was useful to us, but there isn't really such a great solution for this. So every time we add new data, we keep changing the schema every time. And let's say now we wish to model exoplanets. These are planets that are around other stars other than the sun. In that case, okay, now we're gonna, probably just give up, because our schema is gonna have to change again and again and again. So we see that essentially there's a lot of kind of inflexibility when we're modeling data like this in relational databases. If we compare that with a graph, with graph data, we can just start with a node, add another node, add an edge, directed edge between them, label the directed edge as, for example, parent. And we can continue just adding edges between existing nodes, or adding new nodes with edges, new edges, and so forth. So we can just continue adding more and more information in a more flexible, organic way. And this is because we don't need to maintain a relational schema all the time. So we can keep adding more elements. Okay, so now we have this problem that we saw before, that here we say that Pluto is an instance of planet, or type planet. Now Pluto, it's 2006, Pluto is no longer a planet. So what do? Well, it's fairly straightforward. We remove this edge, and if we like, we can add a new node, dwarf planet, and say that Pluto is an instance of that instead. And let's say we want to model other exoplanets, or we want to model galaxies, or other types of information. That's the problem. We can just continue adding new nodes and new edges, and in that way continue to model the data that we wish. So we see that it's somehow much more flexible, sort of data model. Other things are that later in our query language, we can more easily query for paths. So, you can find the shortest path between nodes. You can find paths between nodes, or nodes that are connected by paths that match certain expressions, such as parent followed by child, or we can find the shortest path between Pluto and Milky Way, for example, or Pluto and planet. So there's various advantages to modeling data as a graph. And we can continue adding new nodes, adding new edges, and so forth, building a pretty complex graph of data. So comparing relational data to graphs, some pros and cons are that in the case of relational databases, they're still useful. It's not that we should always use graphs. In the case of relational data, the disadvantage is that we have to impose a structure or schema from the start. And the benefit is that, well, our data have to follow that structure or schema, which means that we somehow have more structure in our data, right? Because we have to follow the definitions of the tables and the attributes of the tables, and the keys and so forth. So it's somehow this sort of top-down, you define a relational schema and all your data must follow from that afterwards. So it's somehow a more strict type of data model. On the other hand, for graph data, the advantage is that we don't have to impose a structure or a schema from the start. So if we don't know, this is particularly great. If we don't know what we're going to model at the start, we don't have to sit down and design that or schema. We can just add data more organically. And the disadvantage is that, we don't have a structure or a schema imposed from the start. So it can be difficult to define sometimes what's in a very large graph of data. because there's no natural, description of the schema of the graph. It can be very diverse with different types of nodes and edges all mixed together in the graph. So it's more flexible, and it's not that it has no structure, in that we would assume as people add data, they try to follow the conventions that were used before. So that should essentially give a more emergent sort of structure. So for example, that, use the instance label for saying what type of node something is, what type of entity it is. Use the, consistently the parent and child relations in a similar way. And that way a structure can emerge in a more natural way from the graph. It's not defined at the start, but rather if people follow the same conventions over time, then you'll have a certain structure that makes it relatively easy to query the graph. So there's no structure imposed, but it should emerge ideally. Any questions or doubts?
Yeah, sorry.
Yep, go ahead.
I have a question.
Sure.
Is there any implementation instead of just a structured database? But in a non-structured database, like for example, as Mongo?
Yep. So you have NoSQL systems that offer different different types of models. In NoSQL systems, you have key value stores, which are essentially dictionaries or maps where given a key, you can find a value. Very simple, but very scalable and easy to distribute over multiple machines. And you also have document stores like MongoDB, Elasticsearch, CouchDB. These allow you to store effectively documents, like can be text documents in the case of MongoDB, JSON documents, and allows you to do search over those. You also have graph databases that are very similar to what I'm describing here, things like Neo4j. And also the systems here that, what we'll see in this course can also be considered NoSQL. In general, I would say that graph databases are a bit closer to, they're somewhere between relational databases and NoSQL stores. So NoSQL stores, often the query language is kind of limited, or it's kind of specific to a particular type of application. For example, key value stores or stores like Cassandra, these tabular stores, they don't allow joins. In the case of MongoDB, you can sort of do joins between JSON documents, but it's not really, it's not so natural, let's say. So graph databases, they tend to implement the full relational algebra, so we can do joins and negation and this sort of stuff, and also implement paths. And another benefit in particular of Sparkle is that it's all standardized. So it's been standardized, defined, analyzed, and so forth, whereas the query languages for systems like MongoDB are more, I would say, ad hoc, like created by the developers of MongoDB. So there's a variety of different options for that. Graph data in general, as a model, is sufficient to represent relational databases. So you can represent all of the data you want here, which if you just have trees, for example, like XML or arguably JSON, it can be difficult because you can't really represent these sorts of cycles in a neat way, right? So in the graphs, you can represent directed cycles. So there's various advantages and disadvantages. In other cases, using MongoDB might be a good option. But what we're really aiming for here is to have a flexible but sufficiently general data model to cover the web, right? So it's sort of like, we're not thinking about creating an application and what database do we choose, but we're really thinking about what's the most general and flexible way to model data in a generic way. And there's multiple answers to that, perhaps, but the answer that the semantic web community has kind of opted for is this graph structure. Not sure if that answers the question.
Yeah, thank you.
Okay. I can also plug the other course that we talk about NoSQL systems a lot in procesamiento máximo de datos, the other course. But more questions or doubts? Okay, so there are some details. There are some details that we need to add about this graph structure. So the graph structure is pretty much the core of the RDF data model, but we have to be careful about naming things. So if we consider that we're going to be modeling data at the level of the web, you know, certain names here might look ambiguous, and it's going to be problematic because there's going to be confusion if we combine it with other data or other graphs from the web. So for example, Milky Way, this we know as the galaxy, but there's also a chocolate bar called Milky Way. Don't know if they sell it here, but and Pluto. So Pluto, okay, we know that's the planet, but we might also confuse it for the cartoon dog. So yeah, if we imagine later, maybe we have some other source of data on the web. Okay, here we want to describe the planet and we want to describe galaxies and so forth, right? The reason why this is dotted here, by the way, Sarah, is to say that we could add this, but we could also maybe at some other stage infer it because parent galaxy implies galaxy. So this could be implicit or we can make it explicit in the graph. So in any case, here we're describing planet. The planet Pluto, and here we have another source on the web, which is publishing data in RDF about the cartoon dog. Okay, so what happens if we were to take data from both of these sources? We might end up with some interesting conclusions. So we see Pluto's a cartoon dog and Pluto's owner Mickey Mouse. So we could, for example, conclude that there is some cartoon character that's orbiting the sun at a very wide orbit. Or we could also maybe conclude that Pluto is owned by Mickey Mouse, for example, if we were to just naively combine the graph. So strings are too ambiguous to use as identifiers in the graph to identify these entities. So rather than just using simple strings like Pluto or Milky Way, we use special identifiers in RDF for entities. So since we're on the web, the idea is we're going to use web identifiers. So what does this mean in general? There are three types of identifiers that we'll speak about here, web identifiers. So the one you're most probably familiar with are URLs, Uniform Resource Locations, or locators. So this is the location of a resource on the web. So for example, this identifier here, with this ugly percent encoding, which Google Chrome and many browsers now hide, but this is essentially the location of a web page, of a document on the web. But what if we wanted to identify the actual city? This is Dublin in this case. So if we want to identify the city, we can use a URI, which is not a location of something because we can't locate a city over the web, right? Or we can't return a city if we're given the URL, right? So this is for things that can be returned over the web. This is for identifying, we can use it for identifying arbitrary things. These are URIs, or Uniform Resource Identifiers. So we can use this URI here, for example, to identify the city. It looks exactly the same. It's just that it's not going to give a 200 OK and return the city directly, right? It might redirect to a page about the city. And finally, we have IRIs, which are Internationalized Resource Identifiers. So these are URIs that allow Unicode characters, so we don't have to worry about this ugly percent encoding here if we decide to have an accent on one of our letters. So IRIs allow Unicode and they don't have to be escaped. So this is essentially for giving the locations of documents on the web. This is for identifying arbitrary things. It's a generalization of URLs. And this is another generalization of URIs, which allows also Unicode characters. So we can do away with this horrible percent encoding. So in RDF 1.1, in the most recent version of our RDF, we can use IRIs to identify things. And one of the benefits that we'll see later in the course is that if we identify things using IRIs, we can look them up on the web to get more information about those things. So how does it work? We'll have an IRI to identify a city, it could be Dublin in this case. Since it's very long to write these sorts of identifiers, we'll often just use an abbreviation, like a prefix, for a namespace. So here EX will define to be a prefix for this URL here, and Dublin is called a local name. So it's just a sort of something we've defined within what's called this namespace of ex.org, example.org.
Professor?
Yep.
When you define that in that way, you are defining like a pair key value, like a prefix and a local name?
Yep. So in this case here, when we define the prefix, it's essentially a key value. So we would say this prefix ex colon has this value. In this case here, the ex colon Dublin is not really a key value thing, because this EX, we could have Dublin, we could have Santiago, we could have different countries defined under the EX prefix. So really, it's just a kind of a shortcut. If we are defining, let's say, lots of cities with this sort of pattern, or lots of entities, can be also countries and planets and whatever we like, we can use this string, this prefix for this. So this is part of the syntax, but as well for the slides, if I start writing out these full IRIs, the slides will get really messy. So there's lots of syntaxes that we'll talk about later that allow for these sorts of abbreviations. It's something I'll use as well in the class. So we can only have one IRI associated with each prefix, but here we can have multiple names under local names with a given prefix.
Thank you, thank you.
Okay. So there are some standard prefixes that I'm going to start to use, and we'll talk about them later. But there is a standard prefix for some core RDF terms, which is defined here. XSD, which we'll describe later, RDFS and OW. So these are kind of prefixes that are related to standards that define some very standard terms that we can see. We can use in RDF, or are frequently used in RDF, but we can define our own prefixes as well if we want. Yeah, so we're going to move now from this idea of simple strings, and we're going to start to use IRIs. Okay, and here again, you have to imagine that this EX really represents some HTTP : / it's really a web identifier. What about the population? Why don't we give an IRI here? Why didn't we identify this with an IRI? We identified everything else with IRIs. And here, this is a special term defined by the RDF standard to describe the instance of something. So RDF type is often used in RDF documents. Why a number here and why not an IRI? Well, we can take a break, and we can have a look at that afterwards and answer that. So we can take a break until 10:55. Any questions at the moment?
Yes, I have a question, teacher.
Yep.
What happened with the same object but in a different page, with a different EX? For example, Pluto, the dog in Wikipedia, and Pluto in an encyclopedia. I don't know the name of that.
Sure. No, I understand the question. It's a very good question. There are ways to link them, and there are ways in which we can figure out that they mean the same thing, but we need to introduce other aspects for that. Essentially, the idea would be, if you wanted to integrate this sort of data across the web, would be that they at least offer a link. The most common way is they either use existing identifiers like DOIs or ISBNs for books. So the different websites specify common keys, or they point to a common location and say that this is the same. So if you describe your Pluto on your website, you could say that this is the same as this Pluto on Wikipedia. And if other websites also point to let's say Wikipedia, there are other options, DBpedia, Wikidata, to disambiguate their entities, then you can somehow use Wikidata as a bridge to say what things are the same and what are different, which Plutos are the planets and which are the cartoon dogs, for example. This is something we'll cover later in the course.
Okay, thank you.
Other question? Okay, so see you soon. We'll take a break and I'll describe this, what happens with the million and numbers and Booleans and so forth after the break. Okay, if not, I'm not sure why I jumped there. Excuse me. Okay, so why not assign IRIs to numbers was the question. And intuitively, it's because we want our data to be machine readable. But effectively, a number already is machine readable in that a machine can say if one number is less than another, it can add two numbers and so forth. So really, there's no need to assign identifiers. They already identify themselves if we give them a type. So we have a second type of term, a second type of element in RDF aside from IRIs, which are called literals. And these are used to represent effectively things like numbers or Booleans or dates and so forth. Things on which machines can operate and apply different types of functions and ordering and so forth. So how we represent these in RDF is we represent these with literals, which can also assign a type. So this might also be, misinterpreted as a string rather than a number. So we also need to identify what type of data type it is. So literals are for data type values like strings, numbers, Booleans, dates, times. They're only allowed in the object position. This is actually kind of a controversial thing. Some say they should be allowed in the subject as well. So in summary, we can use literals in this position here only. So this is okay, and these are not okay. These are not valid RDF triples. So we can only use these things in the object position. Some argue that this should be allowed, but at the moment it's not. So data type literals, they have the form, a general form of having a lexical string, and then this double caret symbol, and then an IRI that defines the type of the data type. So this says, for example, that we have 200 and we have this XSD. Again, this is an IRI. Int, which defines that this is effectively an int. So it should be interpreted as a number effectively. This says that this is a date. This says, this is a Boolean value indicating true. And this is a string. So there's an important difference between, for example, 200 int and 200 string. They don't mean the same thing. For example, 99 is less than 100 only if it's a number. If it's a string, then 99 is greater than 100. So for this reason, it's important that we specify the type as well, which tells us how to interpret the lexical string as a value. So if the data type is omitted, which it can be, then it's automatically assumed to be a string by default. So 200 is a string, not a number in that case. So what data types does RDF support? So the people defining RDF, rather than define, all these different types from scratch, they just borrowed them from an existing standard for XML schema. And there's quite a lot of different types. So we have actually a tree of types where we have some base types here, like string, decimal, different types of dates that we'll see. But we also have derived types. So within numbers, we have integers, non-positive integers, negative integers, non-negative integers. For example, we might say an age property must take a non-negative integer, and so forth. So we have all these different types and different types of strings as well, although these are more rarely used, I would say. So all of these are just imported from this existing standard called XML schema. So what types are there? Very briefly, I'm not going to get into too much detail, but we have Booleans, which can have lexical forms like true or false or 1 or 0. We have numeric data types, and here we see which ones are derived from which other ones. We have decimals, integers, longs. So decimal is kind of any number at any precision. Integers, longs, which are longs like in programming languages, ints, shorts, bytes, non-negative integers, positive integers, and so forth. And then we have not derived from XSD decimal, but we have doubles and floats. And the reason why these are not derived from the XSD decimal is that doubles and floats are floating point representations of numbers. So they're not exact. They're essentially an approximate value. So for this reason, they're not under decimal, these are all sorts of exact values. So yeah, the most common ones here used are just integer and decimal, really. But we can also maybe say, for example, if we're dealing with the ages, that this would be non-negative integer, for example. And we see, okay, what we have here are different examples and some comments about, when they're suitable to use. We have temporal data types, which are to do with times and dates and so forth. So we have a way to represent time in a standard way, which can also have a timestamp with Z indicating, the 00 timestamp. We can have dates. Again, dates can also have time zones. We have date times and date time stamps, with the difference being that in date time stamps, the time zone is required. And this is useful for ordering. So for example, if I tell you, is 8 p.m. today less than, did it come before or after 9 p.m. today? Well, that depends on what the time zone is of 8 p.m. and 9 p.m. So with date time stamps, we have a total ordering, which is nice. Durations. How long something lasted, for example, we have a data type for that, and we can specify that as day times, how many days, minutes, hours, minutes, seconds it lasted, or we can say year, month, for example. We have also data types to represent recurring days, a recurring date, for example, the 15th of every month, to specify a month, for example, December, to specify a month day, which would be like a birthday, for example, 29th of February in this case, 1st of March, a year, and a year month. So these allow us to specify different temporal values. Some are more used than others, like, date time stamp are very commonly used. We also have a bunch of text and string data types, which are mainly listed here for completeness, but they're rarely used. The most often used is just string. We also, maybe have some interesting data types for IRI strings, which allow any IRI, effectively, any valid IRI, for HTML text and for XML data. But these are less commonly used. String is the most common. The rest of these here, to briefly explain, relate more to XML syntax, very rarely, if ever, used. This is for binary data. Okay. So aside from data types, we can also specify that a string is in a given language. So this is very useful on the web, where we're often going to be dealing with multiple languages. So we can say Ireland has name Ireland in English and Irlanda in Spanish. And this tag here with this @ symbol and the tag specifies the language. So we have string and language tag. So if we want to specify a language, there's no data type, because we can't really assign a language to numbers, if we're writing out the actual numeric value. So it's only something we can associate with strings. So we use these standard language codes to identify that. And this is quite nice because it allows us to represent the structure of the data as sort of here in the RDF, but then we can give, you know, different comments and labels and so forth for nodes in different languages. Excuse me. Any question or doubt? Okay. So the third type of term that we have in RDF is then the blank node, which is sort of the most obscure. So we have three different types of terms: IRIs, literals, which we've seen, and blank nodes. So blank nodes essentially are like this concept that, you know, having to name and identify everything can be a lot of work. And sometimes we'd rather just not have to name everything. This might be because there are certain things that are maybe tricky to name, or maybe some things we don't know the value of. They exist, but we don't know what they are. So blank nodes allow us to skip naming something effectively. It allows us to create this node that doesn't really have a name. These blank nodes represent that something exists in that position, most often used to avoid giving an IRI. So it can only appear in the subject or object position. So we can't use a blank node as a predicate. So this is valid, but this is invalid here. We can't have a blank node predicate. So I'll talk a little bit more about blank nodes in a little bit, how they're used and so forth. They're used for modeling more complex forms of data, or they're convenient for modeling more complex forms of data. So we'll return to that in a little while. But for now, leaving them a little bit mysterious, if we summarize the RDF terms, we have IRIs, which we can use to name generic things, not just documents or web pages, but also cities and countries and events and so forth. Literals, which are used to identify data type values, or optionally languages, strings in different languages. And these slightly mysterious blank nodes that we'll return to, which we use to avoid naming things. They're sort of like placeholders in a way in the graph. So in summary, subject can be IRI or blank node, predicate can be an IRI, and the object can be an IRI, blank node, or a literal. So before we get into a little bit of detail with blank nodes, we can talk about modeling some data in RDF. And I claimed earlier that we can model pretty much arbitrary data in RDF. So we could try to model something in RDF. We could take some description of some text and see how we could represent that data or that information as RDF. So Sharknado is the first movie of the Sharknado series. It first aired on July 11th, 2013. The movie stars Tara Reid and Ian Ziering. The movie was followed by another one called Sharknado 2, the second one. So how could we represent this sort of information as RDF? And this is sort of more or less what the lab on Wednesday will be about. We'll give you some text and you'll have to choose that. So the first would be to identify the different entities that will form the nodes in the graph, the different types of relations. For example, stars seems to be a relation that we'll model as a property. The different data types. For example, here we have a date. We shouldn't assign that an IRI, but rather use the XSD date data type, and so forth. So in general, okay, this is something we could maybe have done on the board, but we can jump and see a possible answer here for this. So we have Sharknado series. Okay, first thing is we know it's of type series, so we need to make that explicit. And then we have a first movie called Sharknado, and we have a second movie called Sharknado, which we identify as Sharknado 2. We give the name of Sharknado 2, Sharknado 2, the second one. So here, this is the string, which is the name of the movie, and this represents the actual movie. So it's important in general, if, you know, this is really just a string in a particular language, it's not a movie. So we should try to avoid, for example, just saying second movie Sharknado to the second one, right? We should really identify that with a node because it's a movie and we might want to specify more details about it later. So it's important here not to just give a string as as the second movie. The second movie is really a movie and that deserves a node. We can then say that the node is of type movie. We can use the Rdf type property for that. And then for Sharknado, we have the name, the title here again. We have the first aired, which is July 11, 2013. We should specify the proper data type for that so it can be interpreted as a date, which will allow us later to apply functions like extract the year from the date, order different dates and so forth. And then we have information about who stars in the movie, the first movie. So that's Tara Reid and Ian Ziering, and these are actors. And ideally, okay, we should add that, their names are Ian Ziering and their name is Tara Reid. So, but it would make the graph a lot messier if we start defining all the different labels. So this in general seems to represent more or less all of the information that we have here in the description. So, okay, there's, in general, we see that, it's sort of more or less intuitive how we've modeled this data. So it's maybe a slightly easier example, maybe. So we could try to think about later modeling some more complex examples. Any questions here about this? Okay, of course, there are some differences. We might consider, for example, modeling some of these things in different ways. Like maybe we don't call this property stars, but we call it cast or something different, right? Maybe there's some other different ways to model which movie is the first movie and which movie is the second movie, but this seems to be a reasonable way. Okay, this is maybe the most debatable part of this model is this first movie and second movie, because this will be harder to query later. If we want to find all the movies of a series, it will be like, what's the first movie or what's the second movie or what's the third movie? So we'll talk about different ways of doing that later.
Excuse me?
Yep.
I have a question related to, is there any kind of standard or array agreement about, for example, in this kind, we're talking about, in this example, we're talking about movies. I don't know if there's a standard how to represent this movie, because, for example, I imagine that we can represent many things around the web.
Yep.
So it could be good, for example, if I name stars for the property of the actors, that every movie in this representation also follow that rule.
Yep. So there are not really standards, but more what we would say are de facto standards. Or so there is, for example, a movie ontology. It's not been standardized by the W3C, but essentially the idea is that if enough people use it, then it makes sense to use it because your data will be more compatible. So you have specific ontologies and vocabularies I will see later in the course for specific types for representing data about specific types of things like movies or music or people or, many different types of things, also biological domain, for example. And you also have more general ontologies or vocabularies like schema.org that we mentioned in the first class, which tells websites what vocabulary to use. If you have a cinema webpage, what vocabulary to use to describe the movies that your cinema shows or the products on your website. Only a very few are actually standard, like as in really standardized by a standards body. Most of them are published. Someone creates them because they don't think there's a good model or vocabulary or ontology kind of describing, what properties, what classes to use, which I'll describe in a second. But so the answer is that yes, and the idea is that it's more or less flexible and open, and people can define new sort of vocabularies or ontologies, or they can use existing ones. you can also map between the different ones. So you can say, you know, data described in this sort of vocabulary here, we can model it, we can map it to this other vocabulary in this way. So it's much more flexible, right? There's no top down, there's no body saying this is how you describe a movie, right? It's more de facto standards that, you know, if enough people start modeling movies in this way, it's expected that other data sets would follow suit. So that's something it's a very good question, something we'll come back to. Any other questions or doubts? Okay. So we have two different types of concepts here in terms of how we've modeled movies. The first thing is the list of properties that we've used, and these are typically known as the terms used as predicate. So these are the properties we're using, and this somehow outlines how we're describing the movies. This list of properties is somehow very important, and you know, if other websites use the same properties in the same way, that would be great, because now we can integrate the data more easily. We also have classes, which are these sorts of these general groupings of things, like we have actors, we have movies, we have series. This is also an important aspect of how we're modeling the data. So these properties and classes then form a sort of vocabulary of movies, you know, the terms we can use to describe movies. And for classes, we use the built-in Rdf type property to say that something is an instance of a class. For example, Sharknado is an instance of a type of movie. Okay, so we saw a couple of, we saw a large example of modeling Rdf. We'll take a smaller example here. So Batman Returns stars Michael Keaton in the role of Batman. So how would we model this in Rdf? Okay, so what we could try to do is something like this. We could have Batman Returns as character Batman, played by Michael Keaton. Does this seem okay? So it seems relatively intuitive and straightforward, but maybe there's some complication here that we're not considering, right? So, okay. What happens if we have another movie that also has the same character of Batman? So in this case, well, we could think about representing our graph like this, right? Just adding more data, and now we have Batman Returns as character Batman, Batman Begins as character Batman, Batman played by Michael Keaton, Batman played by Christian Bale. What's the problem here?
Maybe it's that it looks like both actors played Batman in both movies.
Yep. So, or maybe even we could say, you know, so we could interpret it like that, or we could say, even if they played, if we know they played one in one movie, we don't know which, right? So more generally, it's sort of, we know that they played this character, but we don't know in which movie Michael Keaton played Batman or Christian Bale played Batman. So this is sort of a problem, right? So how could we resolve that? Well, we could try to do something maybe like this. So we could say, do the same thing like we did before. And now we add that Batman Returns stars Michael Keaton and Batman Begins stars Christian Bale. And therefore we could kind of more or less assume now that Christian Bale played Batman in Batman Begins and Michael Keaton played Batman in Batman Returns. But, right, we can think of a more complex example where, you know, we have Batman Returns stars Christian Bale in the role of Robin, and Batman Begins stars Michael Keaton in the role of Robin. Okay, so now it's sort of like Michael Keaton and Christian Bale are in the same movies and they play the same characters, but in reverse. So in this case, it wouldn't be sufficient, right? It's getting a little bit hard to model all of this. But now essentially both of the actors are in both movies. And we don't know which one played which role in which movie is the point. So this sort of model then breaks down, you know, so we need to sort of maybe anticipate these sorts of things and try to try to have a more general model, right? So, okay, this is not the case. These are hypothetical. The first two facts are real. These are made up, but it could happen, right? So how we do this is, in general, we need to think about modeling these n-ary relations, which is to say that graphs are very good for modeling binary relations. For example, Batman Returns stars Michael Keaton, right? But if we want to say Batman Returns stars Michael Keaton in the role of Batman, this is a little bit trickier to do. So what we can do always is create a new node. And in this case, I've used a blank node because it's sort of, this blank node represents the participation of Michael Keaton in the movie Batman Returns. So essentially, you know, it's still an entity. It's just a more abstract kind of entity. It's like the participation of an actor in a movie, right? So we could identify this with an IRI. We could say, example, Michael Keaton in Batman Returns, but it's sort of, okay, maybe a little bit more convenient to just put a blank node there. So we can use these blank nodes, and then we can represent. Turning a relation into a node allows us to easily represent the n-ary relation. So if we wanted to add more information about how long this, you know, this character played by this actor was on screen, or in what position of the credits they appeared, we can just continue adding more data here. So in this way, we can represent n-ary relations in graphs, and this allows us to represent pretty much any sort of, you know, anything we could represent in a relational database, we can represent with this trick. And really, you know, this node is an entity, right? I mean, there's not, you know, this, we could say John, so we could say, for example, you know, we could take any binary relation and we can just turn it into a node, or any relation, turn it into a node, and then we can associate more than two things with that relation. So this is a common trick for modeling more complex data. Modeling in RDF is not always so simple. Another downside of the graph model. Oh, sorry, any question here or doubt about this?
How does this relate with the ternary, no, the triple? How is this a triple?
Right, so every edge we see here would be a triple. So B1, movie Batman Returns, would be one triple. B1 played by Michael Keaton would be another triple. B1 character Batman, and so forth. So we would have 1, 2, 3, 4, 5, 6 triples in our RDF graph. So every edge here, every kind of arrow here would represent a different triple.
Okay, thank you.
Okay, any other questions? Okay, so one of the disadvantages of graphs as a model is that they're not good for representing order. There's no order here between the different elements, right? So what happens if we want to represent, you know, something with order, a list of things? So the first movie in the Sharknado series is Sharknado, second one is Sharknado 2, third movie is Sharknado 3. So there's a couple of ways we could do it this way. This is kind of fine, but it's just awkward because if we want to find the movies of the Sharknado series, now we need to do this awkward first movie or second movie or third movie or fourth movie, you know, so that's not so nice. Maybe there's other ways to model that. But is there a more general way to represent lists as a graph? And RDF proposes something called collections, which allow us to effectively create a linked list structure where we say movies and then we point to a list. And then that list then gives an element and points to the rest of the list, which points to an element, points to the rest of the list. And then the list, the empty list nil can be used to end the linked list. So effectively, this allows us in a graph to represent order by using the directed edges of the graph. So what this effectively says is the Sharknado series, The first one was Sharknado, the second one was Sharknado 2, and the third was Sharknado 3. Although it says here first every time, this is just the first element of the list and the rest is here. So essentially, if we follow the entire structure of the linked list, we'll see this the first element, second element, and third element of the list. So we can represent order. It's just a little bit awkward, right? It's sort of like we have all of these triples to connect, and we need these blank notes here. Well, we could use IRIs here as well if we wanted, but typically we'll use blank notes to connect the structure. So this is one thing to notice here is that I'm actually using RDF terms. So this is something that's defined by the standard to represent ordered collections, ordered lists. So by ordered, I mean not that they're necessarily sorted, it's just that the order here really is represented. So we can say this is the first element of the list, this is the second, and this is the third. So this is not just for the Sharknado series. We could also, for example, represent that lemonade has the ingredients sugar, water, and lemon. Right? So we can use the exact same pattern to represent arbitrary lists. It's not that something we just invented for the Sharknado series, although that would be a worthy reason to define it. We can use it for arbitrary lists of things. So here you see that the kind of blank notes we use as kind of glue nodes. We don't really care how these nodes are identified. We just need them to glue together this linked list structure.
Teacher, I have a question.
Yep.
Yeah, regarding the, I don't know, the name of the blank node, that's not important, right? That could be anything.
Yeah, exactly. Yeah. So that's a very good question. Something I'll talk about in the class as well. But these are local names. So they only within a document. It's sort of like the variables in the local variables, let's say of a class in Java or Python. They have a local significance. But in general, at the level of the web, their labels don't matter. They're arbitrary labels. And we'll talk a little bit more about that. Yeah. So these labels, they have no real, they're just used kind of to refer to the blank node in the local document or in the local graph, but they don't have any real significance. Yeah. So I'll be a bit more specific about that later. Actually, I'll finish on this. On this note, we'll finish the class on Wednesday, but these two different graphs we have here for modeling lemonade, both say that essentially lemonade has the ingredients of sugar, water, and lemon. In this case, we use this RDF collection, and in this case, we just say lemonade ingredient lemon, ingredient sugar, ingredient water. Which modeling is better, do you think? Is this way of representing lemonade better than this way? Or this way better than this way? So we see
the second one.
Yep. So the second one is a lot more concise. We'll have 1, 2, 3 triples versus 1, 2, 3, 4, 5, 6, 7. And this will be a lot easier. If we just want to get the ingredients of lemonade, this will end up being a lot easier to query, for example, later when we look at query languages and so forth. So this is a lot simpler and more concise. So that's definitely a positive for this graph. The benefit of this graph here is that we have order. So if we were to consider maybe lemonade as a recipe, and we were to say, okay, we should add the sugar first and then the water and then the lemon in that order, otherwise it will taste horrible. You know, if somehow the order here of sugar, then water, then lemon makes sense, then this is a better model, right? So if the order of the ingredients matters, the collection above is needed, right? We don't have any notion of order here. I've drawn it in, you know, lemon here, sugar, water, but that's just the way it's drawn on the slide, right? There's no ordering here. Here is the only option for, or this is there are other options. This here, between these two options, this is the only one that represents the order of the elements. So if that matters, this is better. Otherwise, if you don't care about the order, this is much better. This is just much simpler. It's going to be much easier to query and so forth. There is one other added benefit aside from maintaining the order of these elements, sugar, then water, then lemon, which is that we close the list, which kind of says, okay, these are all of the ingredients of lemonade. It's sort of like explicitly closed, and it says this is all there can be. So in some very rare cases, collections are used also because they're closed, and it's sort of like this is all there is. Yeah. But that's a very rare, even if you don't care about the order. Yeah, so you have lemon and sugar and water, but you want to say that these are all of the ingredients and no other ones exist. Then, you know, in some cases it might make sense to use a collection, but I would not recommend that in general, because the cost of this sort of more complex structure is not worth it. It's much better to use this more simpler modeling here. So unless you need to maintain the order, sugar, then water, then lemon, this is much better, and this will be important in the lab as well. So you need to decide if you really want to maintain the order of the elements or not. So I will stop. In some cases, I'm probably not going to finish within an hour on Monday. So we can finish the class on Wednesday morning before the lab. There's about 10-15 minutes left of class, and then we can jump into the lab. Any questions or doubts for the moment? So the last part of the class is just to speak a little bit about blank notes and why they make things more complex, and then to look at syntaxes, how you actually serialize RDF graphs. So we can finish that on Wednesday before the lab. So the lab on Wednesday will be giving you some text like we saw with the Sharknado thing, and you'll have to design an RDF graph for that in Turtle syntax. So if there's no questions or comments, see you on Wednesday. Okay. Bye-bye.
Okay, see you. Thank you.
Bye.
Bye, sir. Thank
Hey.
you.
Bye-bye.